Hi, this is Physics 1A for April 29th. Today we're going to be talking about torque, angular acceleration, and how they're related to each other. And we're going to be talking about rolling without slipping. I have a feeling we will not get to the second topic. The first topic is a pretty big topic in and of itself. But if we do get to the third one, the second topic, then we'll talk about that. At least introduce it. Okay, so we've learned about torque in this class. And let me just pull this one over here. We're doing this problem first, so we'll put it right there. So we've learned about torque in this class, and just to remind you guys what torque is, because maybe it's been a while. If I have some point that we call like an axis of rotation, and I have, like an object, like let's say you have a lever or something like that, like a bar, then you can define this thing called torque, where if you say you put a force down like this on this object, and there's some angle here that we call phi, and then you define a vector like this that you call the radius vector, then the torque that gets produced in this case is a vector that's given by r cross f, and the magnitude of this vector is just basically r times f times the sine of the angle, phi. And what we've learned about torque in the past is that for equilibrium systems, oh boy, I'm writing kind of bad right now. For equilibrium systems, we learned that there's something we can do, and we can say that for equilibrium systems, you have this statement that if you sum up all the torques that are acting on your system, those torques are going to sum to zero. That's one of the first things we did in this class, was define what torque was and then use equilibrium in week 2 to solve problems using this as one of the conditions. What we want to talk about now is when a system's not in equilibrium. That is to say, so if the net torque that acts on a system is not zero, acting on a system is not zero, then we want to talk about what happens. And specifically here, what happens is that we get a new statement about what happens with torque. When you have a non-zero net torque, that means you're going to have some torque acting on a system. Okay, I'll give you a simple example of this. Suppose that I have a bicycle wheel, right? And let's say that I take my hand and I just, apply a force in this direction, right? So I apply some force in that direction on my bicycle wheel, okay? And let's say the wheel is just mounted at some point right here so it can't move. You guys know that force is going to have the effect of causing this bicycle wheel to rotate, right? That force is going to make it rotate in a circle. And suppose you take your hand and you just keep hitting it right at this location here, right? So you just keep speeding up the bike by imparting it with just a force, right? That force is going to cause the wheel to spin, but it's also going to cause the rate at which it's spinning to go up. Would you guys agree with that statement? Every time you hit it, it's going to go faster and faster and faster. And that means you also have some kind of angular acceleration that gets produced here. That force, due to the fact that it's acting at some point right here, exerts a torque, and that torque produces an angular acceleration. And it's going to cause the wheel to speed up. The relationship between how that torque produces this angular acceleration is, well, torque is related to angular acceleration by something we learned about last time, which is called moment of inertia. This relationship right here is an expression of how torque produces angular acceleration. If the net torque is zero, the object doesn't move. If the net torque is not zero, it's going to accelerate. You can compare this almost exactly to the linear version of this equation, which is Newton's second law, which is that the net force acting on a system is equal to mass times acceleration, okay? A is replaced with angular acceleration alpha, mass is replaced with moment of inertia, and force is replaced with torque. And that's all the theory. Your book does this whole derivation of where this comes from and stuff like this, but I don't think it's hard for you guys to understand that if you push on something that can spin, it's going to accelerate, right? It starts off at rest, you push on it, it spins. It's accelerating, right? You do this every day in your car, right? You you drive or you ride a bike or whatever, you push on the pedals, it accelerates. It starts off at 0, and then you start moving, right? I don't think I need to derive this for you. I think it's better to just think about it as being torque produces angular acceleration, forces produce linear acceleration. Does that make sense to you guys? Okay, so given that we have this kind of new equation to work with, and there's other forms of this equation, right? And I'll just tell you real quick. There was another form of Newton's second law that we learned, right? We haven't used this very much, but maybe you have, I don't know. The other version of Newton's second law, does anyone remember what the other version of Newton's second law is? If you put a derivative over here, what goes inside the derivative to make this equation true? Yeah, momentum. So force is equal to the time derivative of momentum, right? There's also a version of this over here, but what would we need? Like, just look at the first two equations. Force, torque. Force is linear force. Torque is like rotational force, right? Linear acceleration, angular acceleration, right? Linear acceleration, angular acceleration. This is just acceleration in a straight line. This is just acceleration in a circle, right? Or rotation. You've got mass, and you've got the rotational equivalent of mass, which is moment of inertia. So if I wanted to get a version of Newton's second law that looked like this, I would need a rotational version of this guy, right? And P is momentum, so you need a rotational version of momentum. And if you've taken a physics class before, you may remember that's called angular momentum. So we'll derive it later, and we'll talk about it. There is going to be another version of this that corresponds to this equation here too. All right, so let's take this equation, and let's use it to solve this problem down here. This is a direct application, pretty simple application of where we can use this equation. It's not the simplest problem we could do, so it's a little more challenging, but it will provide kind of like the details of when and how we would use this. Okay. So the Atwood machine shown is a solid uniform cylinder that has a mass of 4 kilograms and a radius of 20 centimeters, with a cord that has a 3 kilogram and a 5 kilogram block attached at each end, passing over the cylinder. So the cylinder itself here is basically a pulley that it has an axis where this little red dot is, and it's able to rotate. I don't know how well you can read that. Maybe I should enlarge this just a little bit here. It doesn't make it much better, but this is 5 kilograms, and this one is 3 kilograms, and then this one has 4 kilograms, and then you can see that the radius here is 20 centimeters. Hard to see within all that stuff. So let's make our own picture. So we've got our circle, and wrapped over this or cylinder or whatever, it has a center right there, and wrapped over this, we've got these masses, right? So I've got one mass over here, and this mass, oh man, is 3 kilograms. I'm going to call it M1, so I'm going to say M1 is going to be 3 kg. I'm going to define the mass of the cylinder, just as it's done in the problem right here, to be 4 kilograms, and we're going to call that big M. And then M2 is going to be the other one, which is going to be the 5 kilogram one. Just so I don't have to write the units every time we put the thing in there. So this rope, it wraps over my pulley here, just like this. And then comes down to here. And that's M2. This is big M. And then we have a radius, R. And R is going to be 20 centimeters, which is 0.2 meters. Now, to solve these kinds of problems, we're going to do something that we've done many times in this class. We're going to draw free body diagrams for each object, okay? We're going to label the forces acting on them. I think it's probably okay in this position to kind of label the forces on the objects themselves. So there's going to be two forces acting on M1 here. There's going to be its weight, which points down like this. You know what? I'll just draw them slightly off to the side because I think that's going to start looking bad. There's going to be a force that comes up this way, some kind of tension in the cable. Let's just call it T for now. And there's going to be the weight of M1 pointing down. No other forces acting on this one. Over here, on M2 is going to have a weight going down this way. And it's going to have a tension that goes up this way. I have to ask you guys, do you think that tension is going to be the same as the other tension? What do you guys think? We've done problems like this before, right? Why not? We know it's going to accelerate because this is 5 kilograms and 3 kilograms. It's going to have to accelerate in this direction, right? And this one's going to have to accelerate up in this direction. Now, the acceleration should be the same because it's just one chord, as long as the chord isn't slipping. But what about the tensions? Could the tensions be the same? Yep. Let's see. Because the masses are different, they're pulling on each other with different forces, therefore... I don't know that that necessarily logically follows, but I think you're on the right track. You are saying that the tensions are different, right? Yeah, you're right. The tensions actually are going to be different. Let's draw one more thing here to see if we can understand why they have to be different. Now, if this was a massless pulley that had no radius or whatever, the tensions would be the same, by the way. But here they're going to be different. So if we think about the forces that are acting on the pulley now, and these ones I will draw here. Yeah, I guess blue's fine. Blue on black doesn't show up very well. We'll use blue, that's fine. So the forces on the pulley would be like this. So I'd have a downward force like here that I could call T. I'd have another force over here that would point down that I could call T, right? But if those were the only forces on the pulley, it would be balanced, right? The only way that would happen is if they had equal weights. This is where I think you're kind of on the right track here with what you're saying that, Ash. If these weights were equal, certainly you could imagine the system would be balanced, right? And then the tensions could be the same. But in this case, one of them has to be bigger because we know that this object is actually rotating this way. It's going to have some angular acceleration. And the only way that can occur is if the tension on the right, which I'm going to call T2 now, we're going to call that one T2, and the tension on the left, which I'm going to call T1. It has to be the case, and here I'm going to do a little erasing to fix this. It has to be the case that T2, well, you guys tell me, should T2 be greater than T1 or should it be less than T1? How should they be related? Like, it's either going to be T2 greater than T1 or T2 less than T1. Which one of those has to be true? Yeah, because we want it to rotate this way, right? So let's draw this vector longer, okay? Now T2 is greater than T1, and yeah. You guys have any questions about that? Are there any other forces that are acting on this cylinder? I left something out here, which is there's a ceiling, right? And then this cylinder is hinged right here, and it has a cord that attaches up here, right? So what other forces would be acting on this guy? On the cylinder itself? Right? So we got another tension here. We'll just call this one T then, because we haven't used that yet. Yeah. Okay, we're going to have to be kind of something like that, maybe. In reality, if I wanted to draw this to scale now, I'd have to draw this tension T bigger, so I probably will do that just to make it look a little bit better. So this tension is going to have to actually be really great, because that tension is actually going to have to be equivalent to T1 plus T2 plus mg. So basically, this vector, this vector, this vector, like they have to sum up to T, right? Does that part make sense to you guys? This pulley still has to be subject to, it's not moving, it's just rotating. So it's in equilibrium, effectively, from a linear perspective. It's not in equilibrium rotationally, though. It is rotating. It's just not moving. So let's use our free body diagrams here to write down some equations. So for M1, we're going to basically say that this direction is going to be positive because that's the acceleration direction. That means that we can say that T1 minus M1G should be equal to M1A. I left out a step here. This is going to be sum of all forces acting on this object is equal to its mass times its acceleration, and I guess we call that the y direction. So then we would say T1 minus M1G is equal to M1A. And then for M2, That's one where we're going to say basically sum of all forces acting in the y direction for that is going to be equal to m2 times its acceleration. It's accelerating downwards. That direction becomes the positive y direction for this one. So we write m2g minus t2 is equal to m2a. Now, up to this point, we haven't done anything different than we've done before. Do you guys have any questions so far? So let's see if we can squeeze the last line right over here. This ended up not being true. The last one is going to be this equation. So this is going to be the net torque that's acting on our cylinder should be equal to the moment of inertia of the cylinder multiplied by its angular acceleration. Now, it's a solid uniform cylinder, and I believe we learned last time that the moment of inertia for such an object is equal to 1/2 mr squared. So it's going to be 1/2 the mass of the object times the radius squared. So we know what I is. And in terms of torques, so let's draw some lines here. That's the radius r. There's a right angle right here. This is also the radius r, and there's a right angle right there. So the torque from T2, why don't we write it like this? Let's do it in 2 steps. There's going to be the torque from 2 minus the torque 1, tension 1 and tension 2. And that should be equal to I, which we said was 1/2 mass times radius squared, multiplied by alpha. The torque 2 would be equal to just T2 times R. And torque 1 is going to be T1 times R. And the reason why it's negative, is because we're effectively going to define this to be the positive direction for torque, because that's the direction that the object's accelerating. That's obviously something we've been consistent with. The direction of acceleration needs to be positive. It's accelerating clockwise, so clockwise is positive. So positive is clockwise. That's why this one's positive and this one's negative. And yeah. Any questions so far? Okay. So now we're in a situation where I think we have 4 unknowns. And I'll write down what they are. These are your unknowns. T1, T2, acceleration, and angular acceleration. Alpha. Those are our unknowns. And I think we only have 3 equations. We have equation 1, we have equation 2, and we have equation 3. So we really can't go any farther here until we can get one more equation, right? Some kind of a relationship between any of these variables. What would another equation be that we could use? Okay, that's another equation we can use. But it's gonna introduce a new variable. Yeah, so good idea. We could definitely use that equation to find tension, T. But we'd still have too many unknowns. What's another equation we could use? Let's think about these ones up here. Are any of these things related to each other in any way? Tension 1 and tension 2, there's no way you could know how they'd be related, right? Until you do some kind of calculation. But what about the other 2? What about A and alpha? Are those related in any way? A is the linear acceleration, for example, of the mass. Alpha is the rotational acceleration of the cylinder. Could those be related in some way? They're related to each other. You're right. This thing is the rate at which the rope is moving downwards here, for example, is going to be the tangential acceleration of the cylinder. Someone just throw me a notification. I missed something. I can see that, chat. I'm sorry, I wasn't looking at it. Okay, let me answer some of these questions really quickly here. If you do forces in the y direction are factored by the masses for mg, wouldn't it make it different, greater? And then Nate said their correct equation, A equal to R alpha, tension from hanging, T3 and weight. Those are the answers. The other, your other question, B, I'm just trying to answer. If you do forces in the y direction, are factored by the masses for mg, wouldn't it make it different or greater? Different. You were talking about the tensions. Yeah, okay. Sorry. I'm really sorry I wasn't looking at it. Thanks for giving me the notification to remind me. I thought I had the right thing pulled up. Anyway, so the relationship is the tangential acceleration of the rope is related to the tangential acceleration of a point on the pulley, and the relationship is going to be that A is equal to R times alpha. That's the relationship we have to use here. And you'll have to do this. We'll have to do this on any problem like this, basically. You'll always have to make this replacement here. So just keep that in mind. That the rotational quantities, like alpha, and the linear quantities, like A, yeah, they were always related to each other. So now we can solve. Let's do that over here. So now let's this equation is going to become, you can see there's an R on both sides, right? It's going to become T2 minus T1 is equal to 1/2 of the mass. There's one R left over that I didn't cancel out, but now alpha we can replace with A over R. All right. And then, personally, I think the easiest thing to do would just then be to take these equations and add them together. So like take this equation and this equation and then just sum them. So we're going to sum up these three equations that I'll put in a different color here. Those three equations are what we want to sum up. If we do that, this is what we're going to get. So looking at the equations, there's a T2 here that's positive and a T2 here that's negative, a T1 that's positive, a T1 that's negative, and then everything on the right is going to add up together like this. So we're going to have on the left-hand side M2G minus M1G is equal to, everything has a factor of A in it here, so it's basically going to be M2 plus 1/2 of big M plus M1, and all of that is times A. One of these radius cancels out here. So our final answer then is that the acceleration is going to be equal to M2 minus M1 divided by M2 plus M1 plus 1/2 of the mass of the pulley. And that's times, oh, that's it, that's the answer. Oh, times G. There we go. Does that make sense to you guys? M2 is 5 minus 3, so that's going to be 2. M2 plus M1 is 8 plus half of, so 10, right? Right, 8 plus 2, yeah, 10, and then G here. So the answer is approximately going to be about 2 meters per second squared, or G over 5. Let's just say G over 5. That's fine for an answer, right? It's approximately 2 meters per second squared. Seems similar to a lab manual homework that you did. Yeah, did you have a lab manual homework problem that was like this? Or are you thinking about the early pulley problems? Definitely did a lot of pulley problems. Okay, that's how you use the angular acceleration. We're going to do another problem that's a little bit more challenging, but do you guys have any questions? I see people typing, so I'll wait a second. The last equation seems similar. Yeah, I mean, this kind of equation is really common in these type of classes. Notice that, by the way, if you were to say, okay, what would happen if the pulley was massless, then this term would be gone, and your equation would be what you would normally get in a system like this. Hope that process makes sense to you. I know this stuff is very challenging, and I think I gloss over details and stuff, so if there's anything I did that you don't understand, let me know. Why did we not include T and mg in the torque equation? That's a great question. So the reason why we didn't include them is because, I didn't even say this, I'm so sorry, I completely glossed this over. This was our axis of rotation right here. The pulley is rotating about that axis right there. So when we do torque, you have to include the force times the distance that the force is away from the axis. So in this case, this one's right on the axis, so it doesn't actually make it rotate. And mg's right on the axis, so it doesn't make it rotate. That's the reason why. But we could have done another equation here. Someone, I think it was Ash, said that if we did want to have another equation here, our other equation would be net force acting in the y direction on the pulley should be equal to 0. And that would give us the last equation, which is basically that T is equal to T1 plus T2 plus big mg. And we could use this to solve for this tension if we wanted to. We're also supposed to find the tension in each chord. And I don't see a reason to do that. I mean, it's just a matter of taking, well, like this equation, for example, and then just plugging in A. And you guys can do that yourselves. It's not a big deal. It's also not hard to do. Maybe I should just do it. It's not that hard to do. Here. So our equation is what? M2G minus A should be equal to T2, right? So that's going to be M2, which is what, 5, multiplied by G minus A. So let's just take G equal to 10. And then G is 10 minus 2, so this would be 10 minus 2 meters per second squared. So what, 5 times 8. So T2 is about 40 newtons. And then T1 is going to be like, from this equation, I think T1 is going to be equal to like M1 times G plus A. And so T1 is going to be equal to, not M, it's, this is M1. Yeah, T1 and M1 were together, right? So this would be G plus A, so 10 plus 2 is 12 times M1. This is 3, so it's basically 3 times 10 plus 2. So that's 36 newtons. No. Well, it is, but... Oh, that's good. We wanted T1 to be... Right? We wanted T1 to be less than T2, so this is good. Just making sure. So that's T1. Okay? That makes sense? Okay. Let's do a slightly trickier one. Now, at the end of class last time, we were talking about when you roll these objects down ramps, like which one gets to the bottom first and stuff like that. Did anybody manage to get a chance to try that at home? With, anyone? No? The thing I asked at the end of class was what happens when you take a... Just to remind you, it's been a couple days, so... you take a ramp, right? And you put a hoop, and then you put a solid disc on the ramp. So you put, like, I don't know, like... You watched his lecture videos about it? Oh, okay, that's cool. You did solve for your final? Okay. I don't know that we're actually going to get there today, because I realize we need to do this one. And this might have to be something we wait to answer until Monday, actually. So, all right, let's look at this problem. How are the due dates looking for the homework, by the way, before I keep going? I just want to check with you guys, because I haven't gotten any requests in a long time for extensions, and that surprises me. Yes, Mastering Physics, yeah. And which one is it? Oh, circular motion. We were way past that. Okay, that's fine. But if you guys do need an extension, just let me know. Well, all the due dates have been pushed back, but we did circular motion, I want to say, 2 weeks ago? No. Was it last week? Was it right after spring break, or did we do it right before spring break? If it was last week, this due date's fine either way. So if just whatever. I mean, the biggest thing is I will still give you guys extensions. I just need to know in advance. It's a lot easier for me to just know beforehand if that's not enough time, and then I can just extend it for the whole class, and that generally saves the time of getting the individual messages, which can be pretty time consuming for me to get into the website. So if you guys are good with it being due tomorrow, I'll leave it that way. If you'd prefer for it to be due till Sunday, yeah, we'll just go to Sunday. Okay, remind me at the end of class and we'll do that. Okay. All right, so let's get this problem done. This problem is quite tricky. Yep. So a rigid rod, okay, with a mass of 360 grams and a length of 1 meter, has a small block of mass 100 grams attached to the end. Do you have a math exam today? Okay, well, good luck on your math exam. The other end is attached to a frictionless pivot that allows the rod to rotate in a vertical circle. The rod starts at rest when it's horizontal. Okay, so does the system make sense to you? The one thing you can do to kind of to understand what's happening here for yourself is if you just take your pencil and you hold it at one end and you keep the pencil horizontal to the ground, right? Just like that thing is, and then just allow the pencil to swing down. That's basically what we're going to be looking at here. Okay, so this object basically is capable of swinging down like this, but it's fixed here. That point is fixed. That's where the axis of rotation is. Okay. So let's get a picture we can play with here. Let's start off by drawing our rod like this, and then we'll draw a little mass at the end. Whatever, it doesn't have to be perfect. It just has to be some kind of mass over here. And this one we're labeling, I think we're going to call this one I don't know. I guess we can just call it M1. And then, let's make that one little m. And just don't worry about this. We're going to make this one big M. Okay? And I'll label what I mean over here. So this is going to be the mass of the rod. That's the, 360 grams. I'm just going to say 0.36 kilograms to get it in SI units. Little m is going to be the mass of the block, which is 100 grams. 100 grams would be 0.1 kilograms. And then let's label all other stuff. L is the length of the rod. That's 1 meter, which is going to be nice for calculations. And that's it. Yep. First thing that it tells us to do is to find the moment of inertia, I, about the pivot. The pivot is right here. We want to find what is the moment of inertia about that pivot. I would say it's going to be the moment of inertia of the rod plus the moment of inertia of the mass at the end. The moment of inertia of a rod, when it's swinging about its end, does anyone remember what the value is? It's something times the mass times the length squared, right? Let me label the length on here too. This is L. What is the moment of inertia of this rod? It's the 1/3 one, that's right. That's all I wanted to see was just the fraction. Yep, 1/3 ml squared. The moment of inertia of the mass is just m times the length squared. It's a single point object. That's what it is. M times the distance from the point squared. Okay, so that's the moment of inertia about the pivot. We can calculate what this is, because I'm pretty sure we're going to have to end up using this quite a bit in this problem. What's up? It just says a small block of mass. If we wanted to know if it was a sphere, we'd need to know something about its radius and stuff like that. So what I'm going to do is just kind of assume that it's a point. Another thing I want to say, and this is where I can probably go back to the lecture notes from Monday to show you. Remember this problem that we did at the end of class? I don't know if you remember. It was at the end of a 3-hour class, so I'm sure you guys were pretty tired, but we calculated the moment of inertia of something really similar to this last time, right? And in that case, we found the moment of inertia was equal to the moment of inertia of the rod plus the moment of inertia of the disk, right? But then to find the moment of inertia of the disk, we had to do this parallel axis theorem thing here, right? This is the point where it's like people's brains are shutting off because I'm just like highlighting equations and I understand. But the point is, when we did this, it turned out that the fact that it was a disk contributed only 0.5, 1/2, to the total moment of inertia, which was 25.5 mr squared. So the fact that it was a disk, I said, didn't even matter at all. We could have treated it as a point mass and got rid of that term. Does that make sense? So that's basically what we're doing here. We're saying, whatever's going on in this problem, it just says small block. We're just going to treat it like a point mass because we have no reason not to. This kind of stuff is going to happen in your guys' homework problems a lot because people like to write these physics problems in ways that are kind of cryptic. And certainly this one's cryptic too, right? So we don't know what it is. We're just going to call it a point mass. Okay, so let's keep going here. We found the moment of inertia about the pivot, but we didn't calculate it yet, right? So 1/3 times 0.36. I want you guys to do this calculation if you could. You can see what all the values are. I'll write them in here, but if you guys could do it for me real quick, that would help. Length squared, that's easy. That's 1 meter, so it's not going to really do much. And then plus 0.1. And we probably just do this one on our heads, I guess. Times 1 meter. And then squared, moment of inertia about the pivot is equal to. So 1/3 of this is 0.12. I think we're going to get 0.22. And then kg meter squared. Does that look right to you guys? Is it mass dependent? Like if it was a big mass, would it still not affect it much? That is correct, Thea. Even if the mass was really big in this case, like if the value for the mass was really big in this case, we would still use this as a very accurate way to get the total moment of inertia. Yes. Yep. It's not really dependent on mass. It's actually mostly dependent on this quantity here. The farther away it is, right? That's squared, right? So that's the biggest factor, is where it is. And if it was like in the middle, you'd have half as much, or a quarter as much, right? Okay, so that's the answer to part A. So this is part A. And like I said, we're going to use this quite a bit in this part problem. Okay, the next thing we want to do is we want to find the initial angular acceleration. Something to think about there is, why doesn't it just say find the angular acceleration? Well, if it's saying initial, it must not be constant, right? So, in this case, to find the angular acceleration, it's going to be due to forces, right? The forces are going to make this thing rotate. And what we're going to need to use is, we're going to have to use this equation that we just learned about, net torque equal to I alpha, if I want to know anything about what the angular acceleration is. And that means we need to figure out what the torques acting on the system are, right? So let's start labeling forces. We've got our pivot right here, and we've got a weight over here on the right ends. Let's put these forces in red. So this weight is going to contribute a force that's going to go straight down, mg. The mass, m, is going to have a force due to its weight, and that force is going to come right from the center, right? It's going to go down this way. That's going to be big mg. And then there's going to be one more force, right? What's the other force going to be? Torque is not a force. There will be torques, but torque itself is not a force. It's at the pivot, exactly. So you also need to have a force going up this way. And I think, yeah, that's going to be part E that we have to find this force. We'll call it, I mean, we could just call it P, right? Let's call it P. Nah, that thing's labeled as P. We'll call it a normal force. I hate calling everything normal forces, but whatever. Normal, weight. Any other forces? I don't think there are. So now we say, if I want to find the initial angular acceleration, I'm going to have to do this calculation. I'm going to say the net torque acting from those forces that I just described about point P should, it's so small, about point P should be equal to the sum of the torques is equal to the moment of inertia times the angular acceleration. That's our equation. And our torques are going to be, well, this is the direction of the angular acceleration, and we're calling it the initial angular acceleration, so we'll just call it alpha I, which means that's the direction we make positive. So we're going to say our torque for big mg is just going to be mg times this distance, L over 2, plus the torque from little mg, so little mg, but that one's multiplied by the total length L here. We don't need to put angles yet because these are right angles right here. You'd multiply by sine 90. all of that should be equal to I times alpha. Well, this is I about the pivot, right? We actually know what that is. We'll just keep that as IP. We don't need to plug everything in again. And that should be related to the initial angular acceleration of the system. Okay. Solving, right? We get alpha sub I should be equal to all of this stuff, which is basically what? M over 2 plus M multiplied by L. And then we divide that by the moment of inertia about the pivot. And that should give us our angular acceleration. Okay, so this is then going to be equal to G. Yeah, I left the G out. You're right. Thank you. Yeah, both these terms have a G in it. Thank you so much. So alpha initial then is going to be what? M over 2. That's going to be 0.36 divided by 2. What's up? Plus 0.1 kg. L was 1 meter. G is, I guess we'll use 9.8. You got 12.47. Other people, that sounds right to me just from my memory of this problem. I remember getting 12.5 in the past. IP is 0.22. Did anybody else get that same answer? Good. So this is our initial angular acceleration, and we'll talk about the unit real quick here too. So the unit's going to be radians per second squared. How do we get radians per second squared? If we look at the units here, you see there's kilograms here that are going to cancel with kilograms here, right? You've got this meter squared is going to cancel with that meter and that meter. So really you're just left with 1 over second squared. So you have to put in the radian yourself. You'd have to, by hand, you have to figure like, oh, but this is actually measured in radians per second squared, right? Okay. You guys have any questions? All right. So then the next thing to do is to find, part C now says, find omega when the rod is vertical. Looks like maybe someone's asking a question, so I'll wait just a second. How to convert from revs to radians, even though it's not the case in this problem? That's a good question. So to do that, to convert from revolutions to radians, you just need to say that 1 full revolution corresponds to 2 pi radians. And then you can set up a, conversion factor, right? Yeah, no problem, man. Very important to remember this. Okay, part C, find omega when the rod is vertical. All right. I gotta draw a new picture for you guys for this one, I think. So now the system is going to be like this. It starts off here, right? That's the kind of initial system. And we want to figure out what the speed is going to be when it swings basically down to here. I'll do them on the same picture so that we don't take up too much space here. So that's still our pivot. And the question is, what's the angular speed going to be when it gets to here? How fast is it going to be rotating when it gets to that point? Okay? So this is our initial, and then this is our final. And any ideas what we should use here to figure out what omega is going to be? The one thing that we got here, the one we just calculated? That one. How can we use that? This one. That equation would work if and only if this was constant, right? But it's not, and that's part of why we call this the initial angular acceleration. Yeah, that's right. Got to do work energy equation. That's right. That's what someone said in chat. Yep. So let's do it. So now we're going to say work done by non-conservative forces is going to be equal to change in kinetic energy plus the change in potential energy due to gravity. There's no springs in this equation, in this system. Haven't had any springs in problems for a while. Oh, there's not going to be non-conservative forces here, actually. So this is going to be 0, and that's going to be equal to... For kinetic energy now, I'm going to write down 2 terms here. That's kind of excessive, but... is it excessive? There's going to be rotational kinetic energy. And then there's going to be the gravitational energy, which is also going to be kind of complicated, so I'll wait a second on this. So the thing is that this system right here is undergoing pure rotation. Rotation. Okay? It's pure rotation. Its center of mass is moving. Right? Its center of mass has moved. I didn't even draw that in the right place, did I? The center of mass of the system is actually going to be closer to here, isn't it? Right? Because you've got that mass on the end. So the center of mass moved, but the way the center of mass moved is it's only along a circular path, right? Does that make sense? And that means you don't need to include, like, translational kinetic energy. Does that make sense? Like, there's... What's up? So this is going to account for all of the kinetic energy, because it's pure rotation. If it was also translating, then we'd have to include that too, but we don't in this situation. Okay? In order to find the change in potential energy due to gravity here, there's 2 different ways that we can do this. Either we can look at each of the objects separately in order to define what the change in energy is, or we could find the center of mass of the system and then look at the change in the y-coordinate of the center of mass. Does that make sense? So that's what we're going to do. We're going to say total mass of the system multiplied by gravity and then times y final minus y initial. But we're going to do this specifically for the y-coordinate of the center of mass, because that's all we care about is what happens to the center of mass. Yes, if the pivot moved, you'd need translational. Exactly, Via. If the pivot was moving, you'd need to include the translational energy. Yep. Like, if this system was attached to a car, to the ceiling of a car, and the car was accelerating, that's a very good, yeah. I was just thinking about another more likely scenario, which is the one I asked you guys to think about last time, which is where you have an object that's rolling, but it's also moving. And that's what we want to talk about, basically, on Monday, probably. Rolling and translating is rolling without slipping. Okay, getting back to this part is kind of tricky here, so let's work on this. So first of all, we actually need to find the center of mass of the system, right? So let's take a step back and figure out where the center of mass of our system is here. So we have a mass on the end, right? And we've got a mass that you can basically think out as being here. Let's start from the end, okay? And let's find center of mass here, okay? I think I can do this calculation right here. So maybe if we just shift this off to the right. Oh no, I took the G with me. Whatever, I can rewrite that. It's not a deal. Go back like that. So to find center of mass, we'll call it the x-coordinate of the center of mass. We'll define this to be our x direction and say the center of mass is going to be given by. We'll take big M times L over 2 plus little m times L, and then that has to be divided by the total mass. Right? So the x-coordinate of the center of mass is going to be m over 2 is 0.18, and m is 0.1. All of that multiplied by a meter, and then divided by m plus m, which is going to be, what, 0.46. It's going to give us the x-coordinate of the center of mass. Where's my calculator? I don't know. Can you guys calculate that one for me? So let's call it 0.61. Maybe we just call it 0.6. Let's just call it 0.6. That's good enough, right? So that's the x-coordinate of the center of mass. And let's come down here and say, okay, well, I know now that this distance is 0.6 meters out to here. That also means that this distance is 0.6 meters, right? So if I define this point to be y equal to 0, then I would say that the initial coordinate of the center of mass is going to be 0, and the final coordinate of the center of mass is going to be negative 0.6. So this one is going to be negative 0.6. Does that make sense? And we can use this to find our answer. We know that the initial angular speed is 0, and we're solving for the final angular speed. This is basically omega final, is the omega that we're looking for. So let's put everything together here. Let's move this piece to the left-hand side. So we're going to have 1/2. Well, that one's negative, right? This is what we'll get. 1/2 omega squared is going to be equal to m plus m times g, and then times, I'll just write it in here, 0.6 meters. It's negative here, we add it to one side or whatever, and so that's what we get. And then we can solve for omega. It's going to be 2m plus m times g times 0.6 meters divided by I. This was the moment of inertia about the pivot that we calculated earlier. So now we get, what, 2 times little m is 0.1 kg, and plus big M, 0.36 kg, times g, and then multiply by 0.6. Did I make a mistake yet? Please tell me if I did. Oh, there's a square root. That is definitely right. Thank you so much. This is all going to be square rooted. I'm just going to have to zoom out a little bit here. I'm running out of space. And it just looks bad, so. And we're dividing that by the moment of inertia of the pivot, and I believe that one was, there's 0.22 right up there. Put that in here. This calculation's quite challenging. You gotta do a lot of stuff. You got 1.58 radians per second. You can get the radians in by hand. Does anyone else agree? Get the same answer? I'm gonna have to go find my phone. 1 second. Apparently it's in my pocket. 4.99. Let's see. $4.96. Cool. All right. Oops. So this one was wrong. We can leave the unit in there. It's 4.96 radians per second. There we go. Still not done. There's still more parts of this problem. That was just part C. Do you guys have any questions? Energy problem. The fact that the angular acceleration is not constant means that you need to use energy to do this calculation. That's what energy allows you to do. All right, part D. Find the force at the pivot when the rod is vertical. Okay? This one's really tricky here. So we want to find the force here. And I'm going to draw a new picture for this. So let's just come down here. We need that answer, basically. So when the rod is vertical, our pivot is right here. That's point P. The rod is kind of like this, right? And we can start labeling forces, right? I mean, one of those forces is going to be here. We can delete this. We don't need this to be here right now. So one of those forces is going to be pointing right here at the pivot. That's the one we call the normal force. We call it N prime. And then our other two forces, well, since we know where the center of mass is now, right, of our system, we could just say that at the center of mass, there's a force of the combined, weights of the objects going down like this. And that's going to be mass plus big M times G. All right? So now we need to figure out how these forces are related to each other. So the first question I would ask is, do you think that the normal force up here is just equal to this weight, maybe? Or should they be different in some way? Should these two forces be equal? The total weight versus the force at the pivot. What do you guys think?
I think normal force would be greater.
Why would the normal force be greater?
It's rotation, so there's a angular centripetal.
Right. Basically, at this moment in time, this object is moving with a translational velocity here that's VCM. It's also rotating with an angular speed that we call omega. And as a result of the fact that it's rotating, and it's going to be spinning, it's going to be rotating upwards, that means the acceleration of this object is actually this way. That's the centripetal acceleration of the system. And we know then that if we define that direction to be positive, that if we sum all the forces acting on this system, that it should be equal to the mass of the system, which is m plus m, multiplied by the centripetal acceleration. Now, what is the centripetal acceleration? Well, we learned two different ways to describe this. One way we said was velocity squared divided by radius, right? But the other way we can define it is by taking that radius and multiplying by omega squared, because the velocity is equal to r times omega. And you can figure out this relationship if you just play with those equations. And we have omega, we just calculated it here, so we'll use that. So that's how we're going to get our centripetal acceleration. As far as the net force goes, the net force is just going to be, let's keep with green on this one. The net force is going to be N prime minus total mass, which was M plus big M times G. And that should be equal to total mass, M plus M, multiplied by AC, which we're saying is equal to R times omega squared. And there we go, we can solve, right? So the normal force is going to be equal to, this is when the rod's vertical, it's going to be equal to M plus M, multiplied by, this will add this term to the right-hand side. Sorry, the algebra here might look kind of messy, but I think you guys should be able to follow this. You guys follow that stuff? Let me know if you have any questions. I'm going to start plugging numbers in. M plus M. Okay, R. We haven't even used R in this whole thing yet, have we? No. I just did something wrong. Ooh, I did something confusing. I'm sorry. What is R going to be? Yeah, that's exactly right. It's this distance here. This is going to be what our R is in this case. It's the distance from the pivot to the center of mass. You might call it like distance to the center of mass if you want to, or whatever, but in this case, that is what R is. It's that distance there. So it's equal to 0.6, right? Because that's where we found this. It's basically the distance to the center of mass. So this is going to be times 0.6 meters. And then omega squared. We just calculated that there. This is a really tricky problem, I think. And I think it goes to show you that these rotation problems are not going to be a walk in the park. They're all going to be pretty challenging and tricky. You need to be very careful about the way you address them, and just keep in mind the general rules about like what you can and can't do, and try not to break any of the laws of physics while you're solving problems. It usually helps. This one is 5.87. Wait, what did I do wrong? Oh, the omega squared. That's what I did wrong. This guy right here. That's squared. God, that looks awful. Squared. Try that again. .3? Yeah, that's what I got to. That's right. Unit's going to be newtons. You can check for yourself. Kilogram, meter per second squared. You got this radian thing that's hanging around, but you know what else is wrong? That is not supposed to be squared. That's, I think, where my squared went. Yeah, you can see with the units that wouldn't work out. Okay, you guys have any questions? Let's see, how does this compare? The normal force. Did we already calculate the normal force earlier? Oh, that's the last step right there. My God, this problem is really quite long, actually, isn't it? Okay, do you guys have any questions about this? We'll run through the last part. Looks like Dan's got a question. Oh, wait a second. Why is the normal force greater than the force due to gravity? The simplest answer to that question is because it's accelerating. It's rotating in a circle, which means it's accelerating, and centripetal acceleration points toward the center, so the normal force has to be greater. I can give you a better example that might be easier for you to think about, Kenny. So imagine that you have a string, okay? And on this string, you have a ball, okay? And you're just whirling the ball in a circle. So I've got a ball here, and we're spinning it around in a circle like this, right? It goes up, and then it comes back down. You're rotating it, right? When the ball is at the bottom, right, the forces acting on that ball at the bottom down here would be some kind of a tension force going this way, and its weight going back this way. But it's going in a circle, right? So you actually have to just think about this, just intuition-wise. You can take your any thing with a string and some mass on it. When you do this, you have to pull harder on the object such that T has to be greater than the weight, right? Does that make sense? You have to pull, it's weird, you pull up to make it go in a circle, but I think you can understand that. Yeah, like that makes sense, right? You have to pull, you can physically feel this if you just try it yourself, right? Okay, cool. Good question. So that was the normal force at the bottom, and the final question is find the initial force at the pivot, okay? So that's where we're getting back to this equation here, and I'm going to bring that down here so that we can kind of just force this thing cut. All right, so we want to find that guy now. What is n equal to? That's part D, or part E or whatever. So now we've got a normal force pointing this way. We've got a weight here and a weight here, right? And we've already used this equation about the net torque being equal to I alpha, but we figured out that we didn't actually need to use the normal force for that because it's acting on the pivot, right? So we need another equation. The other equation we're going to need here is going to have to be a force equation. If the system was in equilibrium, the net force would be equal to 0, but it's not. So instead, we're going to say that the net force has to be equal to the total mass of the system multiplied by the acceleration of the center of mass of the system. And the net force, it's going to be related to the direction of the acceleration. So what I'm going to say here is that if we look at our center of mass here, right, our center of mass of this object we found was like somewhere like right here. That's our center of mass, right? It's going to have an acceleration that I'm going to say is going to point down like this, and that acceleration is going to be related to alpha initial. So the acceleration of the center of mass should be equal to the x-coordinate of the center of mass, which is 0.6, multiplied by the initial angular acceleration, okay? And again, this was the xcm. It's this distance here. It's equal to 0.6. So with this replacement, our equation is going to become this. It's accelerating downwards, so we're going to say basically m plus little m minus the normal force should be equal to m plus big M multiplied by the acceleration of the center of mass. So then n is going to be equal to m plus m multiplied by g minus ACM. Did I make a mistake? That force equals this plus m minus m. Okay, maybe not. If you do have a question, please keep asking. Now, we just need to plug in the information we have. So m plus m is 0.46. G is 9.8 meters per second squared. Minus ACM is XCM, which is 0.6 meters, multiplied by alpha initial. Let's see. Alpha initial's right here, 12.5. Your question, Danielle, was if I were to sum torque taking the pivot to be the other end, would that be okay? Yes, you can do that. I think that'll work. We can try it after this if you want. Let's try it afterwards. I'm curious. That answer is almost certainly right. Okay, I just solved it that way, so I'll see if it matches. I think you do get 1 as the answer. That sounds right to me. Is it 1 Newton? N equals 1N. What an interesting equation. Yeah, I'm pretty sure that would work. Your idea would be, suppose that I start from here and I make that my axis, and then I say, you know, do everything we did, but that made the normal force shows up. It should work, yeah, because you know all the other values. I think it should definitely be the right answer to do it the right way. Okay, so do you guys have any questions? Yeah, if you got 0.94, I think that's close enough. Yeah. It does make sense that the normal force went way up, right, Kenny? Yeah, exactly. It's not as much at the beginning, and then it gets bigger as it goes toward the bottom. That's good that you tried it another way and you got the same answer. That's one of the most important things to be able to do in physics is to know a second method to do the same solution and give it a shot. Because if you get the answer right 2 different ways, then it's a very good chance that you actually are correct. That's more of a hint about taking tests, really, but, you know, in general, it's true too when you're doing homework. Okay, I'm going to go ahead and stop the stream. Wait, there's another question. I'll wait a second, though. Cool. I'm just going to stop recording. But